Okay, so hello everyone, I'm Alan. So this is a series of intensive workshop, and today this is day one for this intensive workshop. So in today's workshop, I'm going to go through some examples of calculating some Christopher symbol or coordinate transformation in flat space-time. So first of all, you can find the material or today's examples on Blackboard, and I encourage you to do the exercise together with me. So this is more like a live exercise class while I'm going through every single step together with you. So if you have any questions during this workshop, you can just stop me or unmute yourself and ask questions. So, okay. So first of all, let's just open up. Do everyone open the material for today's workshop? Okay, because I don't have any split screen here, so I cannot show the solution and the material together. So I encourage you to pick up a pen and a paper and do the calculation with me. So okay, let's start. So for the first questions, A1 is basically a question about coordinate transformation from Cartesian to spherical. So it's given that from spherical to coordinate, from spherical to Cartesian, we have this relations. And also the inverse relation, you can easily work this out. Square root. And we have tangent theta equals to z over x squared plus y squared. And also y over x. Okay, so the first question calculates all the transformation matrix. And the transformation matrix is defined to be basically the partial derivative of these two coordinates. So partial x alpha prime, partial x beta. So the prime coordinate is the spherical coordinate, and the unprimed coordinate is the Cartesian one. Okay, so let me write this down as the full matrix. So R at the first row, so we have partial R, partial X, partial R, partial Y, and partial R, partial Z. And also theta on the second row, and also phi on the third row. Okay. Okay, so for the next step, we are going to calculate the derivative. And okay, so let me just show it to you one by one. So for the first one, partial R, partial X, well, just partial derivative. So let me just write down the answer here. And also partial R, partial Y, and finally the last term. By the way, if my handwriting is too messy, just let me know in the chat room. Okay, so for the next term, partial theta, partial x, you can just take the do the chain rule. First of all, okay, so let me write this way. Okay. Oops. Better not write it into matrix form. Let me write it down into more detailed steps. So here is partial r, partial x, partial r, partial y, and partial r, partial z. Also for 1 theta 1 x, we have to use the train rule. Okay. And then, okay, so we have 1 tangent, 1 theta inverse here, and also minus xz over x squared plus y squared to the power of 3 over 2 in the denominator, okay? So here we have, taking the derivative of tangent, we have cosine squared theta here, on the side here. Okay. So cosine theta is just z over r. So we have this term. So eventually we have this one. Okay. So it is a little bit messy, but okay. For the next one, the calculation is very similar. We also have to do the train rule here. And basically, we just need to replace x here to y because all the remaining calculation are the same. Okay, so for the next term, again, we have to do the train rule. And this time, the later part, the derivative is much easier. So we have minus cosine square theta here. Oh, no minus sign here. So, and also 1 over square root x squared plus y squared for the later part. So eventually we have z squared over r squared times square root of x squared plus y squared. So far so good? Okay, good. So it's just some messy mathematics. Okay, so for the final one, we have to deal with this row. So, okay, let's just write it down. Partial phi, partial x. Again, we have to use train rule because we only know the relation of tangent phi in terms of x and y. So we have this one. So tangent phi equals to y over x. So we have minus y over x squared for the later part. And again, cosine square phi for the first part. Okay, so what is cosine square phi? Cosine square phi is basically, well, here. So it's quite messy to write down in terms of x and y. Well, actually we can make use of this one. So for cosine phi equals to x over, well, because when we have tangent phi equals to y over x, we can write down the sine phi and cosine phi here. So finally, we have, it should be x squared y x squared square root of x squared plus y squared. So we have a square here, so no square root. So the x squared term cancels out, and we have this one. Okay, similarly, for 151y, we do the same thing. Okay, except for this time, the later part is 1 over x. So again, cosine square phi is x squared over x squared plus y squared multiplied by 1 over x. So we have x over x squared plus y squared here. And 1 phi 1 set is basically 0 because phi is not depends on set. So okay. So far so good for the first transformation matrix. Oh, by the way, for the newcomers, the material is on Blackboard, so try to do the exercise together with me. Okay, so the first transformation matrix is done. Let's go to the second one. So which is mu prime. So again, it basically is just the inverse transformation. So we have partial x mu divided by partial x nu prime. Just want to ask by the notation of transform. It's like this. Why the notation of transformation is like this? Oh, so are you asking why we have a superscript here and a subscript here? Is that what you're asking? Okay, so you have to take a look on at this guy. Oops. Okay, this one. By the way, that is lambda instead of, that is big lambda instead of eta. Okay. So you know the rules for the indices for upper indices and lower indices, right? So for coordinates, usually we use the upper indices to represent the coordinate. And if we divide by something or do any partial derivative, sorry. So let me enlarge the transformation here. So by definition, the transformation matrix is the partial derivative between two different coordinate systems. So the mu here correspond. Okay, the mu here correspond to the old the x mu, or in our case, the Cartesian coordinate. So since it is located in the numerator, so we keep the superscript for mu. However, for nu, since it is in the denominator, so it is superscript in the denominator. So when we convert it into the matrix, we have to put a subscript here, just like, okay. Yeah, that's the general rules. So let me think whether I can. For example, when we talk about partial derivative, usually in index notation, we write it like this, right? But if we explicitly write down the partial derivative form, it will become something like this. So you can see that the mu here in the denominator is in the superscript. But when you convert into the partial derivative notation, it appears in the subscript. And the reason for that is that because if you are using superscript in the denominator, you are meaning that you are taking something also with a superscript, right? Let's say a mu here. I'm contracting mu and nu. So in that case, in order to for this representation to become a scalar, the partial derivative, the notation for the partial derivative should have a mu in the subscript. So that's the general rule for the index notation. Okay, I hope that that answers your questions. So let's continue. And for this one, again, let me just explicitly write down the transformation matrix. Again, the first coordinate, the first Cartesian coordinate on the first row, x, y on the second row, and finally z on the third row. Okay, and this time the derivative is much easier to calculate. Let me move or copy the definition down here. Okay, so for the first one, it's just sine theta cosine phi. Second one, r cosine theta cosine phi. Third one, r minus r sine theta sine phi. Okay, for the second row, we have sine theta sine phi here, r cosine theta sine phi here. Oops. And lastly, r cosine theta cosine phi here. Okay. And for the third row, well, just the same calculation. And 0 here. R sine theta cosine phi, which term? Oh, I see. Thanks. Yeah, this should be sine theta here. Okay, so yeah, in this case, the derivative is much easier to calculate. Okay, so that's basically is part A. Okay, so we need to express the matrix element in terms of subscripted coordinate. Well, not necessary. Just that you can express everything here in terms of whether Cartesian or spherical coordinate is fine, because well, they are basically the same. It's free to convert one coordinate to the new coordinate system given the relation of both coordinates. And you can see that in these questions, it's much simpler to represent everything in spherical coordinates instead of. Well, of course, you can do this. Of course, you can do this. So now may realize that what I did here is really dumb because, well, we have to write everything in terms of a bunch of x and y and z. But just to show you how to do things in Cartesian coordinate and spherical coordinates, well, I have to do it once. But of course, you can convert everything in the first part of part A into spherical coordinate, and you'll find that the expression is much simpler, much simpler. Okay. So for part B, find the quadratic line element. Okay, let me use another color. Green. Okay. Find the quadratic line element in spherical coordinate. So again, first of all, let me write down the line element in Cartesian coordinate. So it's like this. So the first method you can use is that you can simply write down the relation of these two coordinates. So I believe it should be sine theta. Yeah, sine theta cosine phi, or sine theta sine phi, and finally cosine theta. And take the partial derivative and using product rules. So we have dx equals to blah 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 dr blah 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 d theta d phi, etc. And then substitute this into the quadratic line element of Cartesian coordinate, and well, you can obtain the quadratic line element in spherical coordinate. So, well, how about let me do it once for you. Okay, so this one is dr, and then well, d theta, I'll define, but actually doing this is very dumb because this term we have already calculated it. These are just the element in the transformation matrix we have calculated. So this row represented to this row. So how about let's just use the index notation to do the calculation. So now we want to find G in the new coordinate system, in spherical coordinate system. So let's say G I prime J prime equals to the metric in Cartesian coordinate, and also perform the transformation. Not use I prime here. Well, let's use Greek letter. Mu here, alpha beta here. So alpha mu prime and also beta nu prime here. So the G alpha beta represent the metric for Cartesian coordinate. Well, basically just 1, 1, 1. Okay. So let me write down the full summation for you. So we now have, because we are summing the alpha and beta are dummy variables, we now have to sum over alpha and beta. Does the order of matrix and the metric and transformation matrix matter? It does not matter, and it will become obvious once I write it down. Okay, let me write down the full form for you first. Better not do this because we have 9 terms then. So the reason why the order does not matter is because the tensor component is just a number. The tensor component is just a number. And basically, we are just multiplying 3 different tensor components here and sum them over. And you know that multiplication for numbers are well, commutative. So you are free to swap the number, no matter you write it as this form, or you want to write it as this form, or the other one, or swap the other. It doesn't matter. It doesn't change the result. But yeah, that's right. But if you want to use matrix multiplication, then the order matters. Yes, those are two different things because, but if you use the tensor notation and sum over all and explicitly write down the summation, that the order doesn't matter. But if you want to write it into a matrix form, we express the tensor into a matrix form, then the order matters. And the reason for that is for, let's say, for matrix multiplication, let's say we have two matrices A and B, and if we do matrix multiplication, if I write it down into index notation, the final ij component of the result of AB is this. Okay, because we are the ij component of the final multiplication is just the I summing the multiplication of the I row of A and the jth column of B. So if you want to do the matrix multiplication, your indices must written in this form, which means that in this case, if we want to use matrix to do the calculation, we have to write it down as a form of matrix multiplication, which means that I have to write it like this. The alpha and alpha here, and beta, beta here. And this guy is not the original transformation. It is actually the transpose of the original matrix. So in matrix form, you will see something like this. And depending on your definition of the transformation matrix, sometimes you will get something like this in other books, but this only depends on the definition of the transformation matrix. Okay, so let me do it in both ways. So let's try the matrix representation first. So for the matrix one, okay, let me, okay, the original one is chi theta cosine phi. Okay, let me just copy it. Okay, so multiplied by 1, 1, 1, and then finally multiply by lambda itself. Okay, so this one is, well, basically we just have to take the transpose of lambda. Okay. Let me put it in the next column. How can I realize it should be a transfer from the index notation just because the index are written in different? Yeah, that's true. Because well, you can see it in the matrix using the matrix. So let me explain it more in more detail. Let's say we have a matrix A here, and these are the matrix component. Okay, 2, 3, 3, 1, 3, 2, and 3, 3. So now what is A transpose? Oh, okay, so let me just give one example. Consider only the 1, 2 index and 2, 1 index here. After taking the transpose, the 1, 2 index of A transpose become the 2, 1 component of the original matrix A. So yeah, for rank 2 tensor, taking the transpose in the matrix representation is basically swapping the two indices, swapping the order of two indices. Okay. Okay, next I have to do this matrix multiplication. So first one, second one, third term. Oops. Okay. Well, for this time, it's just one. Okay, let me skip the step here. I believe you all can do matrix multiplication. And for the second one, it should be a 0 here, 0 here, R square. So anyone wants me to write down the detailed step for matrix multiplication? Anyone? Okay, no need, thanks. Okay, so that is how you convert the matrix tensor into another coordinate using matrix multiplication. Or if you use tensor or Einstein notation, we have G mu prime equals to something like this. Okay, so what we have to do is just to write down all the possible summation and all the possible index here. So let's say G1 prime equals to da 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 da, and then you explicitly write down the summation here. But in our case, since the G alpha beta is a diagonal, is just identity matrix, 1, 1, 1 in the diagonal and 0 in the off diagonal term. So we can write down as something like this. G11, G22, and G33 here. And G11, G22, and G33 are basically one. So you just have to calculate this summation for every possible combination of mu prime. And that is actually another way to write the matrix multiplication. So basically, they are all the same. Okay, and for the, okay, I actually did part C as well, the matrix tensor. And for the inverse, I believe you guys all know how to find the inverse tensor. You just have to take the matrix inverse, which is this term in our case. Okay, only for the not only for diagonal, but in our case, since the matrix tensor is diagonal tensor matrix, so we just have to take the inverse of the diagonal term. But in general, that's the inverse. Oh, you mean the element only for diagonal? What do you mean? Yeah, that's the for inverse matrix we only have diagonal term, and that's the, in that case it's just the inverse of the original. Of course, we cannot take the element inverse directly. That is 100% wrong in most cases. Okay, so moving on to part D. Christopher symbol. Is there a quick argument for why metric tensor have to be symmetric, or is this true in general? Well, okay. So far in general relativity, we only consider symmetric tensor. The metric tensor itself is not necessary to be symmetric. You can have non-symmetric metric tensor for the same quadratic line element, and the thing will be a little bit different if you have a non-symmetric metric tensor. So for Christopher symbol, it's not symmetric, and etc. So you have, I believe, Johnny have mentioned that you will have some torsion terms in general relativity, but so far we only consider symmetric metric tensor. So any non-symmetric tensor is not in our consideration right now. Okay, so for Christopher symbol, we have this. That's the formula for you to calculate the Christopher symbol. Okay, so again, let's plot all the things in these equations. First of all, let me copy the metric tensor we have just found in the last questions for the calculation. Okay, so let's just first consider alpha to be the R component, so which is 1 and then mu nu. Okay, so for the alpha to be R component, we just replace F3 alpha in the formula to be 1. Oops. And since we are summing over all row, and we know that only GE11 is non-zero, both G12 and G13 are 0. So we can Well, basically, it's just G11 that matter. So we can, for the next step, we can replace all the row by 1. Oops. 1 here. Okay. And then you can very easily see that for which combination of G mu nu we have non-zero Christopher symbol. Okay, let me write this down. So for let me further simplify this because G11 is just 1. So we can write this way. Okay, so we have gamma 11 to be G11 111 minus 11 comma 1. So which is basically G11 comma 1. But since G11 is 1, taking partial derivative with respect to R is 0, so we have 0 for 1 term. Similarly, for 1, 2 term, again, we copy all the thing in here. G12 is off diagonal, so it's 0, so 0. Again, G11 is constant, so this term is also 0. So for 1, 3 term, 1, 3, 1, 1, 3, 1, 3, 1, and also 1, 3, 1. Again, 0, 0, 0. And next, for 2, 2 term, since 2, 1 term is equals to 1, 2 term, the Christopher symbol is symmetric. We have 1, 2, 1, and this time, these 2 terms are 0, but the last term is not 0. Because G22 is R squared, and taking partial derivative with respect to R, we have minus R here. Okay. So for 2, 3 terms, well, they are all zeros because 1, 2 are 0. Oops. 2, G1, 2 are 0. G1, 3 are 0. And 2, 3 is also 0. Should it be G? Oops, you're right. It should be 2 and 2 here. Thanks. And finally, for 3, 3 terms, again, copy everything in that. And now we have another non-zero term here, which is R squared sine squared theta, and take partial derivative with respect to R. We have minus R sine squared theta here. So now we have finished 1/3 of the calculation. Let me write it down in the matrix form. Okay. So moving on for the next part. Okay, let me continue to do that. Theta mu nu. Again, let me use 1 here and 2 here. Again, half of G2 rho G rho mu G rho nu and minus G mu nu. And again, for off diagonal term to be 0, we have G22 here, 2 mu, 2 nu, and comma 2. So G22 is, for this time, is 1 over R squared, since it is the inverse metric. And okay, let me copy that. Okay, so okay, let me, do you want me to continue to write down all the component, or just write down all the non-zero component? Okay, let me just write down all the component here. So for, okay, let me write it in a more compact form. 1, 1, we have 0, 0, this is also 0. So for off diagonal term, basically just replace it by 0 because it's quite obvious to see that. 1, 2 term, we have 0, 3, 2, 2, 1, and 0. So now for this term, we have partial derivative of R squared with respect to R and 1 over R here. For 1, 3 terms, we have 0, 0, and 0. So they're all 0. Okay, moving on to 2 term. So, okay. G2, 2, 2, 2, comma 2, 2, 2, partial 2, which is, again, all 0 because G22 does not depend on theta. And 2, 3 term, we have 2, 2, partial 3, 0, and 0, which is again 0 because G22 is not a function of phi. And finally, we have three terms. So again, 0 plus 0 minus G, not 0 this time. Because for this time, G33 is a function of theta. So after taking the partial derivative, we now have sine theta cosine theta with a minus sign here. So finally, we can write down the Christopher symbol for theta in the upper indices. It's something like this. Okay, so now we have finished 2/3 of the calculation. Yeah, it's a painful work, but okay, let us continue. For phi, okay, okay, alpha to be phi. Misplaced. Yeah, you're right. It should be the 1, 2 term. Thanks. 1, 2, 1, 2. Okay. Thanks. Okay, finally, the final component we are missing. Again, for off diagonal term, they're all 0, and for G33 is r squared sine squared theta in the denominator. So we have this. Okay, let's do this together. One term. We have 0. Okay, let me drop the first item. I don't want to copy 1/2 r squared sine squared theta so many times. 0 and this one. And it's also 0. Okay, so for 1, 2 terms, so 3, 1, 0, 3, 2, 0, and 1, 2 is also 0. So it's 0. So for 1, 3 terms, okay, so this term is not 0. So now we have 3, 1 to be 0. Oops, sorry. 3, 3, 1, and 0 here. So now it should be r squared sine squared theta. So it is 1/r. You caught me. Okay, let's continue. 2 terms. So 0, 0, 0. Okay. 2, 3 terms. 3, 2 is 0. But we have 3, 3 partial 2 here and 0 here. So we have something like this, which I believe should be cotangent theta. Yep. And finally, 3 terms. Well, since 3, 3, 3 is not depends on phi, again we have all 0 here. And that is the final component of the Christopher symbol. We have 1, 3, 2, 3. So 1, 3, and 2, 3 to be non-zero. Okay, so that's it. So yeah, calculating Christopher symbol is quite a painful work. And in our case, we are doing it in spherical coordinate, which is actually quite a very simplified version to calculate Christopher symbol. So you can imagine that it would be much messier to do the calculation in some more general or more complex metric. But however, I believe I've taught you another way to calculate the Christopher symbol in exercise class 3. I'm not sure whether of you have attend that class and watch the recording. But if you want to know a much faster way to calculate the Christopher symbol, then you can refer to that video. And I believe Harry will teach you that method on Wednesday as well. Okay. So moving on, the next part. Do you guys want to take a break? Or we take a break after part E, because part E is actually quite long. Okay, let's take a break for 5 minutes and we'll continue the workshop on 305. Okay, see you later. Okay, so let's continue to part D. Part E, calculate the gradient, the Gaussian, and the vector divergence, and I believe the vector Laplacian in spherical coordinate. So have you done that before? Have you tried this try to do this conversion before? Changing all the vector operator from Cartesian to spherical coordinate. Have you guys done that before? Yes, really, in which course? QM, okay, quantum mechanics, well, and also electromagnetics, okay. Well, yeah, that's a tough job, especially if you try to do it by writing down all the components, all the vector components, etc. Yeah, that's really hard, but well, luckily we now have learned the Einstein notation and also some knowledge about curvilinear coordinate, and now we should able to, we should able to do this well, much more easily. It's still a tough job, but it should be well, at least that will be fewer, and you can do it a little bit more easier. Okay, first of all, for divergence of f. So let me first write it down into the Einstein notation. So that's basically something like this, the covariant derivative of a scalar function. Okay, so what's that? The covariant derivative of a scalar function. The definition of the covariant derivative. If something is something like this, okay, for scalar function, there will be no Christopher symbol, just partial, just partial D. So yeah, it's simple. So what's partial D? In spherical coordinate, it's just partial R. Okay, partial R, partial theta, and partial phi. Okay, let me write it down into vector form. Partial R, partial theta, and partial phi. So do you guys notice some differences from the original operator we're using? It seems like that we are missing something in these expressions, because if you look it up in the Wikipedia, you can find that the gradient of a scalar function in spherical coordinate is something like this. So why the first expression here is missing something? We are missing 1 over r here and 1 over outside theta here. Do you guys notice why? Yeah, because of the vector. Right. Because right now we are using the natural basis for the first line. In all the calculation we're doing here, we're using natural basis. Yeah. But usually when we do the vector operator, we are doing it in orthogonal basis. Okay, so how to change it back to orthogonal basis from natural basis to orthogonal basis? Do you know how to do it? Okay, let's consider a vector v. So if I write it into the vector form, it's just the component itself multiplied by the unit vector or the basis vector and summing over all the basis vector. And in natural basis, so what is the length of the basis vector? It's just the, you can find from this, from the definition of metric tensor, Gij equals to the inner product of two basis vector I and j. And so the unit vector itself is just the square root of Gii. Here the I, the double I here is not under the rules of Einstein's summations. It just represents the I component of the metric. Okay, so now we can define two things. So let's say here this one is the basis vector of the natural basis, and let's say the unit vector itself is the basis vector of the orthogonal basis. Okay, so we must have one relation, is that this one equals to this one, right? Okay, so how about the vector component? So this one is the length of the basis vector. How about the vector component itself? The vector component, we can, well, again, from the vector, you can write it down as the vector component in natural basis or the vector component in orthogonal basis. Okay. So since we have what we have here, since the vector itself, the geometrical itself is unchanged no matter using whatever basis vector, we must have these relations. We must have okay. So oops. So in vector component in orthogonal matrix, just write the first four letters. Will be to convert it. Okay, I'll write this way. The natural for the vector component itself, the vector component in natural basis compared to the vector component in the orthogonal basis, we have these relations. Okay. So in order to convert everything back to the orthogonal basis, we have to divide everything into divide everything by 1 over square root Gii. Okay, so now we can have the expressions for the gradient in orthogonal basis. Which is something like this. So we now can convert it the feathered component from natural basis to orthogonal basis. Okay, so for this part, the Laplacian of f, so it's just in Einstein notation, it is something like this: the covariant derivative of the covariant derivative of f, and contracting these two components. Okay, or I can, well, write it like this for simplicity, because usually what you have learned is the index in the covariant derivative is in the subscript. Okay, so let's calculate this. First up, in order to calculate something with two covariant derivative, what I recommend is to first of all expand the outermost covariant derivative. So for the first one, the lambda I here, we can write it into the partial derivative of I plus the Christopher symbol K here. Because lambda J, we can treat it as a rank 1 tensor and perform all the should be minus here. Okay. Everyone follow me here. Okay. Well, just stop me if I didn't explain it clearly. And after doing that, then the nabla f is very simple. We just convert it into partial derivative. So what we have here is, okay, let me write down on the next page and expand it. Okay, that's mine. So for GII here, again, in the in spherical coordinate, the metric tensor is consists only the diagonal term. So we have G11, 1, 1 here, and also K11 here, plus G22, 2, 2, F minus, and finally G3, 3. Okay. And so let's just consider the first 3 components. It's basically just 1 over R squared second derivative of r, that should be 1, sorry, g11 should be 1. But for the second one, it is the 1 over r squared partial derivative 1 theta squared f, and finally 1 over r squared sine squared theta 1 phi squared f. Okay, and these terms remaining. Okay, we have to sum over the crystal symbol 1 term, K11, K22, K33. Okay, so let us take a look at the crystal symbol we just found. For terms only consist of 1, 2, 2, and 3, 3. So 1, 2, 2, and 1, 3, 3 are non-zero. 2, 3, 3 are non-zero. And that's it. So now what we have here is the first part here minus 1, 1, 1, I believe is, okay, I forgot. Minus r, okay, minus r sine theta and minus sine theta cosine theta. So we have minus r k, wait, for this one k is 2, and minus r sine theta, okay, sorry, k is 1 here, k 2, 2. I think you missed the metric part. You're right. Okay. Okay. 1, 1, 2, 2, 3, 3. Okay, thanks. Okay, which means that I have to write it in the next line. So for case 1, we have G11. Okay, let me write down all the things to avoid confusions. Two, 2, and 3, 3 here. And then for k equals to 2, we only have 2, 3, 3 terms here, and that's it. Okay. Okay, let me copy this. Okay, so G22 here is 1 over r squared multiplied by minus r plus 1 over r squared sine squared theta multiplied by minus r sine squared theta. So, and then we have partial derivative of f with respect to r. And the final one, G33, we have 1 over r squared sine squared theta. And for this one, I think it should be sine theta minus sine theta cosine theta. Okay. Again, to simplify it, so we have minus, okay, plus 2 over r here, and plus cotangent theta over r squared here. Okay, so for the final step, well, we can embed it this term into this term with this one. So if we take the derivative with to r squared, we have 2 r over r squared, we have 2 over r. So we have the extra term here. And for the cotangent, we can write it as 1 over psi partial derivative of psi. Okay. I should write it here. So taking partial derivative of sine theta, we have cosine theta over sine theta. We have the extra part cotangent theta here. And finally, we have this one. Okay, so now we derived the Laplacian of f in spherical coordinate rather quickly. Okay. Right, now but into partial d, but sometimes need to involve the Christopher symbol. Okay, so first of all, do you know what's the difference between the covariant derivative and partial derivative? Partly, I guess. Okay, so let me explain in details. What's the difference between the covariant derivative and partial derivative? So first of all, yeah. First of all, for scalar function, they have no difference. But why in some cases they are differed by an extra Christopher symbol is that when we consider the derivative of the vector field itself. Okay, let me give you an example. Let's consider again in spherical polar coordinate, let's say a constant vector field. Okay, for constant vector field, well, you can imagine that taking derivative in constant scalar field should equals to 0, right? But if we are using polar coordinate or spherical coordinate, okay, that case should be polar coordinate. If we are using polar coordinate, the coordinate basis itself is something like this. So let's say at this point, if we are located at this point using the polar coordinate, the vector should look something like this. Okay. When we take a derivative, we have to consider the change of the vector field in neighbor point, in neighbor observer. So when we consider something like another observer at this point, so since we are using polar coordinates, so the basis itself is slightly differed by the original one. So if I have to draw the new basis vector for the neighbor observer, the coordinate basis would be something like this. So in both, this kind is not good. Okay, it's too light maybe. So let me use red. Okay, draw it again. Okay, so in these two cases, since the coordinate basis, the basis vector itself depends on the coordinate. So if you compare the vector field of neighbor coordinate, the coordinate changes, even though in Cartesian, the vector field is constant. So if you are in the red frame, again, move it back to the original. And if you consider the derivative of vector component itself, it is non-zero because the vector component in these two coordinate bases are different due to the change in coordinate bases or due to the change in the basis vector. So the Christopher symbol is describing, the Christopher symbol itself is describing the connection of these 2 points, which basically means that it considers the change of the basis vector instead of the change of the vector component of the vector field. So that's why we have an extra term for taking the covariant derivative. So for the first term, it is the change in vector component in neighbor basis, neighbor basis. Is it the curve itself is unchanged for both frame? You mean which curve? Are you talking about the vector field itself, or the scalar field, for example? Well, for the scalar field, then we don't have any problem in scalar field, because simply because for scalar field we don't actually need the basis vector to describe its component. So the change in any basis vector, you don't have to consider it when you take the derivative. Only if you take the covariant derivative of vector field or tensor field. Okay, maybe I can draw a better graph. This graph is a little bit messy. Okay, again, consider, first of all, let us consider a constant vector field where it's a point in the z direction. Okay, but if we used spherical coordinate or polar coordinate to view it, okay, let's say the black arrows here is the coordinate for r and theta. Then in this observer or this coordinate, the vector field will becomes a vector pointing with an angle phi with respect to, I think it should be r and theta here. Okay. But if you want to take the derivative of this vector field, we have to consider also the neighbor vector, which means that for another coordinate system, let's say for this one is r prime, r theta prime, then the coordinate basis actually changed a little bit because for polar coordinate basis vector, every point have their own unique basis vector. And in that case, in the right frame, what you see that is that the vector field will change a little bit in this coordinate system. Okay, so if you consider only the vector component of these 2 frames, you think that the vector field itself is changing because the vector component changed in these 2 coordinate systems or in these 2 basis vector. However, well, what we are using here is a constant vector field. So it seems that the change of the component itself is due to the change of the basis vector. Okay, that's why when we take the derivative or the covariant derivative of a vector field, we are not only considering the change of the vector component itself, but we also have to consider the change of the basis vector. So, and that's what the Christopher symbol means. It corresponds to any change in the basis vector. Okay, any questions? Okay, so yeah, that's why the covariant derivative have an extra term. So I think in mathematics there's some fancy name for the Christopher symbol. I think if I didn't remember it wrongly, something like connection 1,4. Connection 1,4. So I think it's a more accurate name for it because Christopher itself is basically connecting the basis vector of two neighboring points and describing how it changed. Okay. Okay, let's move on. We don't have much time. I think we may not be able to do questions 2 today. But okay, let's see. If I cannot finish it on time, I will post the detailed step of calculation and solution on Blackboard later. Okay. For the next one, we have the divergence of vector in spherical coordinates. And again, which means that we are doing something like this in Einstein notation. Covariant derivative of a vector and then contracting the two indices because the dot product here. So that should be fairly straightforward. It'll be something like this. And then what we have is something like this plus summing all the Christopher symbol. And for this term, actually, I think I have mentioned it in probably exercise class 6 about what this term is. It's basically related to the determinant of the metric itself. But never mind, we have already worked out the Christopher symbol, so it would not be hard for us to, do the summation ourselves. Okay, so let me write down all the non-zero Christopher symbol first. First of all, we have 1, 2, 2, 2b minus r, 1, 3, 3, 2b minus r sine square theta, 2, okay. Let me check. 1, 2, 2, 1, 3, 3. Oh, did I do something wrong here? Yeah, I missed the square sign here. Then 2, 1, 2, 2, 3, 3. Okay. 2, 1, 2, 2, 3, 3. And finally 1, 3, and 2, 3. Okay, so for k equals to 1, we have 1, 1, 1 plus 1, 2, 1. Okay, sorry, 2, 2, 1 plus 3, 3, 1. So what we have here is 2 over r. And for II2, we have 1, 1, 2 plus 2, 2, 2 plus 3, 3, 2. And what we have here is, I believe it's just cotangent theta. Okay, my handwriting is a mess. Okay, finally for II3, we have 1, 1, 3 plus 2, 2, 3 plus 3, 3, 3. And I believe it should be 0. Okay, so eventually what we have here is 2 over r VR plus cotangent theta v theta. So to simplify it, it is just 1 over r squared partial r squared VR plus 1 over sine theta v theta plus this one. So that should not be the usual form you have seen, because in this case, the vector component are in natural basis. So in order to convert it into orthogonal basis, you have to divide every metric component by square root, divide every vector component by square root of GII. So in that case, okay, let me write it down explicitly. Over G11, G22, and finally G33. So we have an extra 1 over r here, and extra 1 over r sine theta here. And that should be the usual form of divergence you have seen in orthogonal basis. Okay? Any questions? How do I distinguish? How do we know whether we are in natural or in orthogonal basis? Well, basically, it depends on the metric you're using. So in our case, for spherical coordinate, the metric we are using is this, right? Oh, okay. I should probably add a prime for orthogonal basis. And I will make it more clear. I will upload a detailed calculation step in LaTeX file of this workshop, and I will state it more clearly in that solution. But to know that whether we are using natural basis or orthogonal basis, we simply take a look at the metric tensor itself. Here, okay, Here, the metric we are using in all the calculation is 1 r squared sine squared theta. So the unit factor, the basis factor itself are not a unit factor. So in that case, these we are using it in a natural basis. We are doing it in a natural basis. And you may wonder what the difference between natural basis or orthogonal basis in doing the calculation. But indeed, you can do all the calculation in orthogonal basis with some differences. First of all, in natural basis, okay, let me make a table to make it clear. For natural basis, when we do partial derivative, it is something like this, right? Just taking the derivative with respect to the coordinate itself. But in orthogonal basis, if we want to do it directly in orthogonal basis, we have to divide an extra term here. The reason for this is that, well, in natural basis, what we have, or in general, the line element we have is something like this, right? So in matrix form, for example, in spherical or in spherical coordinate, it's something like this: dr, d theta, d phi. Metric here, and finally dr, d theta, d phi. It's something like this, right? So how about in orthogonal basis? In an orthogonal basis, we require that the inner product of the basis vector itself is unitary. It's 1, which means that the diagonal terms for all the metric tensor in orthogonal basis should equals to 1. But the line element should unchanged in whatever basis or unit vector or the basis vector we use. So if we want to fix all the basis vector to be 1 in orthogonal basis, what we have to do is to change the terms here. So instead of dr d theta d phi, we have dr r d theta r sine theta d phi. And same for this one. And the prefactor in front, the one here, the r here, and r sine theta is here. Right, G will be 111 if we are in orthogonal basis. But the calculation, all the other things, all the partial derivative, and also the Christopher symbol will be different or the how we calculate them will be different. Because the basis here, what we choose in natural basis, or what we usually do to choose the basis is just take the derivative of the coordinate itself. But in orthogonal basis, we have to normalize it by another prefactor. So instead of d theta, we have to use r d theta, which means that if we want to take the derivative with respect to theta, we have to add an extra 1 over r in front. So that's the complicated part in orthogonal basis. Moreover, in orthogonal basis, in order to find the Christopher symbol, we have to stick with the definition of all the Christopher symbol. So for example, I think the definition of Christopher symbol is something like this, right? And of course, in orthogonal basis, you can imagine how things will go in orthogonal basis. Thing will be much more complicated. I put a hat here to represent the Christopher symbol in orthogonal basis. So you can expect that it's much more difficult to find or much more complicated to find the corresponding Christopher symbol in orthogonal basis if you want to use the summation notation directly. But of course, the another way to do it is to first of all find everything in natural basis, and then because we know how to convert it from natural basis to orthogonal basis, we can just take the convert it back to the original orthogonal basis. And yeah, and the conversion is quite hard to picture. And I think I will write more detail in the solution. But hopefully you can get the idea behind. But again, let me emphasize, all the mathematics we do in this course, you can treat it all in natural basis. We will not do anything in orthogonal basis unless we specify, but I believe we won't have any problem about doing calculation in orthogonal basis. The reason why I changed the final answer into orthogonal basis is that it's a much more familiar expression for you guys, because usually in EM, all the calculation you do are in orthogonal basis. But it's fine to stick with the natural spaces as long as you keep all the things consistent. The vector component itself are in natural basis, basis vector itself are in natural basis, then it will be all fine. Okay. And for the next thing, next questions, the Laplacian of a vector. And I don't think you have did this before in EM, simply because it's too complicated to do this. But now we have learned more about the curvilinear coordinate. We should be able to derive it. Okay, again, the same rules. But this time I'm only doing it in natural basis for simplicity. I may convert it back to orthogonal basis in the solution, but for saving times here, I'll just do it in natural basis. And again, always do the covariant, the outermost covariant derivative first. So treat this part as a rank 2 tensor. So this is a rank 2 tensor with an upper index k and a lower index j. And we all know the rules of doing covariant derivative of rank 2 tensor. Okay. M minus ij and kn. Okay, and we can just copy everything and replace t with the covariant derivative. So we now have this term plus I k m, this term minus okay, m I j, this term. Okay. And to simplify things a little bit, well, because you can imagine how things go if we want to expand all the covariant derivative. It will be a mess. But to simplify things a little bit, okay, let not do this first. Let's continue expanding. Well, I thought doing the summation with ij would be a good idea, but okay, just for the exercise, let us continue to expand everything in these expressions. Okay. Minus also masuk M V N. Okay, that's it. Okay, to simplify things a little bit, let me do it this way, just to expand everything. Okay, we have to take the covariant derivative of this term. So we have this and this. Remember, you also have to take the derivative of the Christopher symbol. And then expand everything. Okay. And then we can now do the summation. Again, Gij, we only have diagonal term. So the first thing, the most straightforward thing is 2. First of all, well, let me see if I can sympathize thing a little bit more. Okay, never mind. We have, well, let me just write it down as this first. We have to sum over second derivative of with respect to r theta phi for the first one, vk, and then we also have to sum over rj for the diagonal term. Okay. Oh God. Okay, let's do this. K1m 2m and also 3m. Okay, so that's the first term. And for the second term, 1m plus 2m plus 3m. Okay. And I think this term and this term are the same. So we just have to multiply this term by 2. Okay, this one should be J. And then keep summing it. Okay, so and then we have okay, did I miss something here? Because it seems that this one should be K. Yeah. K, K, K. Yeah, I know this is a mess and I don't really want to do this as well. But okay, let's continue. Plus. Okay, so that's probably it. And the next step, what we have to do is to just plug in all the Christopher symbol in that. Okay. Again, let's first consider K to be R, the first component of the vector Laplacian. Okay, so again, we have this one, V1 here, and for gamma 1, 1, well, it's all 0. So this term is 0. And for gamma 1, 2, we only have two terms, 1, 2, 2 terms here. So we have something like this. And similarly for 1, 3, 3 terms, we only have 1, 3, 3 terms, and 2 here, 2 here. Okay, next, 1, 1 times 0. And we only left with 1, 2, 2 term here, and 1, 3, 3 term here. And since 1, 2, 2 does not depend on theta, I believe it should be minus r, so this is also 0. The 1, 3, 3 does not depend on phi, it's also 0. And finally, 1, 1 is all 0. 1, 2. So it should be 1, 2, 2. The only non-zero term is 1, 2, 2. But for 2, 2, the only non-zero term, let me check, is 1. Okay, so the n here is 1. Okay, makes the vn here. So v1 plus 1, 3, 3, 3, 3, 1, v1. And that should be it for the first component. Okay, maybe, yeah. You can plug it in all the Christopher symbol. Let's go to the K, the second component, K equals to theta. And for this one, it is still a mess, but let me process twice. Okay, for this term, this one is 2, K is 2. Okay, it's better for me to copy all this. V2 plus 2, 1, 2 is non-zero. V2, 2, 2, 2, 1 is non-zero. So V1 here. And 2, 3, 3 is non-zero. So we also have this. Plus, okay, we have V2 here. Okay, not yet. But for 2, 1, 2, it should be 1 over R. So we can, the derivative 1, 1 is non-zero. But for the next two terms, they are all zero. So what we left with is just this one. And finally, plus 212 and also 221 V2. 2 3 3 is non-zero, so 3 3. In this case, both 3 3 1 and 3 3 2 are non-zero. So let me put it this way: 2 3 3 3 3 1 V1 plus 3 3 2 V2. And final terms for K2B. Okay, for the final term, you can't really simplify it. You have to do auto summation. The auto summation remains there. Okay, and I think I forgot to do the last term here as well. But again, it's all summation, so I won't write that down here. And finally, the last one. Okay, again, for the final one, we have V3 here, 3 1 3 is non-zero, 3 2 3 is also non-zero, and 3 3, both 3 1 and 3 2 are non-zero, so we have two extra terms here. And multiplied by 2. And for next 9, okay, 3 1 3 is non-zero, and also 3 1 3 is 1 over R, so it's also depends on R. So let me keep it here. But for 3 1 2 3, okay, for the others they are all 0. And next, K2M. So we have 3 2 3 here. 3 2 3 should be cotangent theta, so it's dependent on theta again. So we keep it here. And finally, both 3 3 1 and 3 3 2 is not a function of phi. So this one is 0. So next, we keep expanding it. 1 3 3 1 3. And next 3 2 3 and 3 2 3 Vn V3. And finally 3 3 1 1 3 3 3 1, and also 3 3 2 is non-zero, so 2 3 2 3 3 V3. And if I didn't remember, 2, okay, the others they are all 0. And again, let me skip the final line. Okay, so after plugging all the Christopher symbol in, you can find the expression for the vector Laplacian. And yeah, it's a mess. And my recommendation for you is to try to learn to write a mathematical notebook and put everything in the notebook and let it do the calculation for you. So far, any questions? Nope. And I think it's already 4 p.m. now. So in that case, I think I should end the workshop here. We're only halfway through the examples. But anyway, I will put the solution on Blackboard maybe later tonight or within this week. So again, I encourage you to try to do the exercise once and try to get familiar with all the calculation. So if you have any questions about this workshop, or if you want to do the workshop another way is in a faster ripples, you can email us or tell us if you want to do another way on Tuesday or Wednesday. Okay, let me stop the recording here.